tells me that I love you more than all those pretty pearly shells. And that's to all my kaina in Hawaii, and my heart goes out to those for their loss in our fires. So, but to go on, I'm going to do a little bit of Racing Against the Sunset by Philip Wessey. That was actually a Bing Crosby song, Pearly Shells, and that was sung in English and Hawaiian. Wesley's equestrian trail.
That was really lovely, Kim. Thank you again so much. And it's great to be back here for another month, everyone. Welcome to the August meeting of Orange County Astronomers. We have just again been treated to a great concert by our own astronomical harpist, Kim Kanahele.
Thank you so much for having me. It's a pleasure always.
It's really great and totally unique, Kim. Thank you again so much.
You're so very welcome.
Well, everyone, I think before I turn it over to, or we get on to the announcements, just a couple of preliminary matters. Some of you may have heard that we had a fire very close to our Anza site about 2-3 weeks ago. And fortunately, it moved away from our site. It turned out to be a fairly lengthy affair before they got it under control. We did not have access. We did not suffer any damage ourselves, but it is a warning that we need to take fire risk very, very seriously out there and frankly everywhere, I think. So please, take precautions wherever you are. And if you're out at Anza, please be sure that any pad that you may be responsible for or any observatory has an area of clearance around it so that it will be at less risk of fire if we do have one that comes over the site. With that, I think it may be time for our announcements. I'm not sure if Sam has them ready to go up. Ground crew? Unfortunately, I had an indisposition today, so I can't be on the ground. So I am joining the meeting remotely rather than being at Chapman, and I'm not quite sure what is going on there. Yeah.
Some years ago, I had a tour of Channel 9 KCAL in Los Angeles, and I got the tour from the director's point of view and the engineer's point of view, and was not able to go on stage. It was not this complicated. Oh dear. Okay, we ready to go, guys? I have 2 blank screens in front of me. Okay, ready? Okay, welcome to the meeting again, as Barb said. And I've been delegated to do the announcement since I'm the only live and sentient person within the range of the microphone. This is a hybrid general meeting. And you need to know that most clubs can't do this. We do it pretty well and been doing it for months. And we actually enjoy it. Again, thanks to Kim for live harp music. I don't think any other club in the country has the access to a wonderful harp player to have introductory music, or the hall, or to you out in the audience, both here in the hall and at home. So hit the space bar. Good. Welcome to new members, Robert Nasu and April Park. Always love to have new members. Be sure and get your badge up here in front if you can.
You need to share the screen.
They aren't showing.
We're not sharing?
No, it's not showing on the
Okay.
webinar.
Okay, I believe Barb said already that we've had some problems out in Anza. Are we on?
Not yet.
Here you go.
Well, if people were paying attention to the pre-show, there we are.
We're getting close. There we go. Are we live?
Yes.
Okay, good. So in case you didn't pick it up at the beginning of the meeting with the rotating slides, Barb, are the dates for Anza Star Party still the same?
They should be. Actually, this month we have 2 Anza Star parties,
Okay.
the 12th and the 19th, because the new moon is on Wednesday.
Okay. Now, what's the condition of the site out there in the
At this point, it is fairly clear there's good access to it. I know Brett has been out there pretty much, I think, all week. Charlie was going to be going out tomorrow, and he was out there last Saturday. The roads are passable. They are open now. And we should be good to go for the star parties, but keep a weather eye out. It's always a good idea to check for what the weather is going to be, because it is getting kind of thunderstormish, and also for any smoke.
Is there actually running water out there?
Yes, there is. That was the other issue this week, and Heritage Well Services managed to clear up the problem that we had.
Ooh, this has not been an this has not been an easy process for us, because there's been a fire up there that's kind of disrupted lots of things. But it looks from right now that August 12th and so forth will be good star parties. In case you didn't know, the Perseids are coming up the 12th. So suggest you go out there and after midnight, keep an eagle eye out and count the little shooting stars as they go by. The astrophysics group of the beginners class and OCA and beginners class are on the back of the Serious Astronomer and on the website. So if you'd like to join those and you're not sure, which I've had a couple of questions this evening about, email or call the person that's in charge of those meetings and see what's going on.
One thing, Doug, sorry to interrupt. There was a change in the astrophysics SIG meeting date to August 25th, not August 18th. Okay. It just got changed yesterday, so it's a recent change.
So if you have your website available or your printed Serious Astronomer, you can call the people in charge of astrophysics or the vice president, secretary. Is that you, Alan?
Yeah,
you can ask.
Yeah,
Alan,
that's me, and it's on the calendar. The calendar's been updated.
And the calendar's been updated. So that's your first line of defense against going someplace where nobody's meeting. I actually went here one night and there was nobody here. So we had our own meeting. Okay, outreach events. Jeff Gray is working on the outreach events, and he's a program coordinator. You can contact him at outreach@ocastronomers.org. Now, our whole club is organized around that one ocastronomers.org. So if you think, what's in the newsletter? Type newsletter, oca.org, and you'll get in contact with the person. So that's one way to make all of this much more reachable. The coffee stand, which I've been calling Chez Helen. I guess maybe I should change it. Coffee, donuts, and water, $1 each, exact change appreciated. Available by the library entrance before the meeting and through the WhatsApp presentation, but not during the speaker. So Helen, are we still in business up there? Yay, good. Chez Helen. If you come up with a really cool name, let her know, okay? Cosmic Cafe, that's been taken though, hasn't it? Oh, okay. All right. Adopt-a-Scope program. Tomorrow is the day, John, is that right? Picking up scopes and dropping off scopes. So do you have any suggestions, John? Hoot? Show up before noon. Okay, that's good advice. That's been a very popular program and very much worth it. People have gotten the scope that they needed, not the scope that they bought or wanted. Oh dear. I think my first scope was a 60 millimeter refractor and I saw Saturn in it and I never saw anything after that. I got rid of it. And then I got a C90. Okay. I had 3 scopes the first 3 months I was in Astronomer. Dave Fisher is our editor for the Serious Astronomer. Turn any information you'd like to have published into him. He's a very good editor. He told me no this week. I turned in some stuff and he goes, well, that isn't quite right. And that's a sign of a good editor. It just, oh, anyway. So you'll see my article someplace else. It's on the website. I didn't mean we'd go to some other club and publish it. Okay, moving along. Delivery preferences. You want to get the Serious Astronomer online? Great. You can request that. If you want to get it on snail mail, you're welcome to do that as well. ANZA site weed clearance. Now, I'd mentioned in the board meetings that some small percentage of the weeds up in ANZA include hemp. So it's possible in your weed clearance, you may be able to make a slight profit from renting your weed clearance machinery and be able to propagate that monetarily someplace else, although I have no knowledge of that. But it is clear, especially in the Midwest, that some small percentage includes hemp. But don't blame me. I may be completely wrong. Okay, is Galileo here tonight? No. You know that Galileo's almost 12 now? He's a young man. He's a big guy. And if he were here, he would say that tonight's moon phase is a waning crescent. It's 21% illuminated. And I suspect John has a little more to say about that. Okay, next meeting will be held on Friday, September 8th. And right now we're going to wait for John Garrett. I warmed up the microphone and burned out the battery, John, for What's Up. Please welcome John Garrett from TVA.
Thank you. That's very nice. And actually, I don't cover the moon in my What's Up. I neglected to do that. In fact, one of the early What's Ups I did for the club, someone pointed out that I failed to cover any deep sky objects. I probably had all moon that time. So I think I've completely switched since then. And we'll have my presentation going in just a moment. But it's really nice to be here. And as long as any of you are meeting in person, I'm so glad to come here in person too. I really like coming here and seeing everyone, at least everyone who can attend. Oh, anyway, so I've really had a nice time the last few weeks trying to prepare for this What's Up, because I did a lot of observing of some new things. And so I'm pretty excited about what I saw. First of all, I wanted to make clear in my own notes, I often garble my explanation of which telescope a particular image is taken with. And so these are the only two scopes that I have that I actually take any images with. One is a 3-inch refractor. The other is an 8-instrument Cassegrain. So all of my image are with one of those two. And sometimes I garble an explanation as to which one it is. Also, last time I was here, someone asked me which software I was starting to use in doing my own stacking. I'm very new at that, and I gave the wrong answer. So I made sure I put in the copy of the software that I actually do use, and I think it's called Deep Sky Stacker. So that's just a preamble to some of the things that you'll see. Okay, this was not taken with any of the instruments I just showed you in the last picture. This was taken with a wide field camera. Just a couple nights ago, we had a rocket launch, and I was late for the launch, but I was more interested to see if there was any atmospheric effects lingering from the launch. And I noticed it was kind of a purpley sky. So all the purple that you see in this picture over the constellation Scorpius is from the rocket plume. And from what I understand, what I've been reading on the internet from other people who are posting these, is that this red is really caused by electrical discharge from the rocket plume to particles in the ionosphere. So it's actually a glowing ionosphere. So that's pretty exciting to see. And then I got another picture of it happened to cross right over the center of the Milky Way from where I'm standing. And here's the characters, Sagittarius and Scorpius, next to that rocket plume glow in the ionosphere. Now, about this time of night, a little bit later than this time now, but if you go that way, follow the arrow behind those trees, you'll come across the constellation Capricornus. And then just beyond that constellation, rising early in the evening, is the constellation Aquarius. And that's where you're going to find our one bright planet for the evening that's good to look at. Saturn is going to be reaching opposition in a couple weeks, and so it's around rising at sunrise, at sunset, and after a few hours it gets up high enough and you'll have the best views of it that you're going to get for a year. I haven't seen Saturn this season, but people who have tell me that the rings, they're starting to notice them a little bit tilted so that you see a little less ring than you did last year. Of course, that's expected. And in the evening sky, just I think it was yesterday or the day before, Mercury had reached its easternmost elongation, which means it was as high in the west as it's going to be. And since then, it's starting to plummet. But this weekend, you might get a chance to see Mercury if you look toward the western sky. And then this picture I took a couple of years ago without the Scorpion. I added the Scorpion to it, but it was a picture I took this time of year of Scorpius, and I captured a Perseid meteor. And so that leads up to the next big event, is that the Perseid meteor shower is this weekend. I like to say my daughter Emma was actually born during the Perseid meteor shower. My wife got a good view of Perseids in the middle of the night as I was driving her to the hospital. There was some contention over which one of us was going to use the little counter. She wanted it for counting the kicks of the baby. I wanted it for counting meteors, but she won. Anyway, so we've got this Perseid meteor. We've got the Perseid meteor shower this weekend. So it's timed really well because it's falling on a weekend, and it's falling on a weekend that does not have a terribly bright moon. So I've really longed for a Perseid shower like this. So I really plan to get out in the desert if the weather, holds up. But anyway, here's you don't have to get out to the desert to see Perseids. They're fairly bright. A couple years ago, I think this was during the pandemic, I just took pictures from my balcony. And so since I was in town, I just pointed mostly up and toward the east, and I captured 5 in the same field of view, which I put together as a composite in this particular picture. And you can trace back the paths of the meteors. And so I captured approximately the radiant point in this particular meteor shower. And here's it kind of diagrammed with some constellations. So down in Perseus, which rises very early in the evening, that's the radiant of the Perseid meteor shower. The Perseids are notable for having vivid colors, often a lot of green in them. And so that's another thing that makes this meteor shower particularly pleasant, especially to photograph. I love photographing meteors. One of the reasons is that if you photograph a meteor, there's a good chance that you're the only one in the world who has that photograph. And so it's a good chance for amateurs to pick up to shine. But not everything that looks like a meteor in our photos is a meteor. So for example, this particular photo that I picked up when photographing a globular cluster, I think clearly shows that some satellites brighten and then dim. And the fact that this one brightened again and then dimmed, I think pretty much sells the idea that a lot of our images that have a brightening and dimming, we may have captured a satellite and not necessarily a meteor. So it's nice to check our pictures for those things. For example, here is one of my pictures that I recently downgraded from meteor to satellite. I overexposed the picture, and I think you can see the continuation of that trail. So what looked like a meteor was actually, when I overexposed it, you could see a continuous trail that works all the way off of the screen on the right. I hope you can see that on the big screen. It shows up pretty well on my small screen. So whenever I take pictures, I make sure to try to prove my pictures wrong to, oh yeah, see if it shows up. I don't know if you can see it, but I can see it now. You can see the whole satellite trail going all the way off the screen, which leads me to another check. If your trail shows up in the following photograph, that's a pretty good sign that you've got a satellite and not a meteor. If you get out this weekend and take some pictures, you'll probably end up with a lot of pictures like this that maybe you'll have a meteor plus, but you'll certainly have a couple satellites. And what I've noticed is that if you zoom in to your satellites, because they're moving slowly, they have the same amount of distortion, at least in my pictures, as the stars do, whereas the meteors stand out as just a little bit crisper. And this weekend, you'll get a very good test of that hypothesis because you'll be able to see green ones. If you capture any green ones, that will then obviously be a meteor, so you can see how they look different from satellites on your pictures. And you will get satellites. There's a lot of satellites up there. I think last year, I was in the driveway photographing, and I actually saw this meteor. This one didn't show up with a lot of color, but it allowed me to put together a little demonstration of something that I've always wanted to test. I've always wanted to, well, you know how you'll see clouds in the evening cast rays of light in all directions. And sometimes if you look in the other direction, you'll see those rays converge on the opposite end of the sky. So I always thought, well, I bet meteors do that, but I've never really spent the time pointing the wrong way through a meteor shower to test that. But I have this one picture I took a few years ago, and I have this one that I took just last year. And if I overlay them correctly, I think they show that there might be a point where the meteors do converge on the other horizon. And therefore, it might be worth my time to set up a camera this weekend that's pointing away from all the action to see if I can capture multiple meteors actually converging toward the horizon, or converging to the opposite point in the sky as the radiant. And another thing I've always wanted to do with meteors, I've read that an FM signal will be deflected by a meteor trail, so that if you have a radio station that is just out of range of where you are, you can tune into that station, and whenever you hear it suddenly come in, that may be because of a meteor. So you could do meteor counts that way. So I did a quick search to find out if I could find a little more information on that. And it turns out the school that my son is going to go to starting in 2 weeks, I'm going to take him there, actually had this little explanation. So I thought that was meant to be. So I stuck it into, I stole it and put it into the presentation. But if you don't get out and you want to try to locate an FM station, assuming you can locate an FM radio, you may want to give this a try. I'd like to give it a try sometime. Anyway, like I said early at the beginning, one time I was chided for forgetting to put any deep sky objects in one of my presentations. So I think I'm going to make up for it with this one. I've been quite obsessed with this area of sky over the last couple weeks. And so it's going to be leaving us soon. So I highly recommend digging into that. And so this is where the constellations Scorpius and Sagittarius are. And here's their commonly depicted constellations. And I was actually surprised at how big of a constellation Sagittarius is. So all of these red stars that I've circled are all Sagittarius constellation stars. And the only exception in that area is Corona Australis, just right below, kind of sticks in there a little bit. But all of these are common Messier objects that can be easily seen. All of these I can see really well with my 8-inch telescope, especially at a dark site. And then it's how well you do with a smaller telescope tends to vary, but many of them you can see at a dark site, even with binoculars. And here's like one example, M7 right off of Scorpius's tail. And here's another couple that I got these in my driveway just last weekend, M8 and M20 plus M21, the little star cluster just above the colorful Trifid Nebula on your right that has the two different colors shining in it. And then this, okay, so these are the Messier objects. I don't have time to show all of them or go into all of them, but this many of them are globular clusters. So I started getting kind of fascinated with globular clusters recently. And here's a classic M4 in Scorpius globular cluster, plus another distant globular cluster there toward the bottom. I think that's NGC 6144. I'm going by memory. I'm not sure of that. And here is another bright globular cluster in Sagittarius, M22, but there's a lot of little subtle ones, and some of them come together in nice little combinations, nice little aesthetic arrangements. So if I were to extend the Messier globular clusters to the NGC catalog globular clusters, there's like all of these to choose from. And last weekend, over the last couple of weeks, that is, I've been able to photograph most of them, and about half of them were just barely detectable by eye in my 8-inch Schmidt-Cassegrain. And but these particular areas were the areas that I discovered for me the first time. They've been discovered by others long ago, but for me, I saw these globular pairs that I thought were pretty interesting. So the first one in the spout of Sagittarius, you've got two globular clusters, very faint, but they are very close together. So there's a good chance that you might be able to see them very close or maybe in a single field of view. And so here they are taken with my 3-inch telescope. And here's another one that I really look forward to trying with my 8-inch when I get a chance, because you've got two globular clusters between two fairly bright stars. So the bright stars will allow me to make sure I can check my focus on my Schmidt-Cassegrain, which tends to get a little mushy on the focus at times. And so I'm looking forward to coming back this weekend and possibly trying to get these objects imaged. And then this was a happy accident. I wrote down in my observing notes that I was going to look at NGC 6558 and 6559, thinking those two were together. Well, it turns out that 59 isn't next to 58. Actually, 69 is next to 58. So I punched in 6558 and got my one picture. Then I punched in 59. I was expecting my motor drive to just do just a short little whir, just a quick little whir to the right spot. And instead it goes, which, made me panic. And, that feeling where you've spent a half hour getting your scope aligned and suddenly it does something like that. You think, oh no, there goes another half hour. But it turns out that I just wrote down the wrong number. And 6559 is a star forming region that you could barely detect in this photo. But down in the corner was a globular cluster. And when I figured out what I had done and what that one was, it wasn't long for me to realize that globular cluster is next to another globular cluster, which is next to M8. So I was able to get all three of them into the same field of view. We often look at objects like M8 and think, oh, well, what else is there in that area? But there's some really nice little globular clusters that you might want to try once you look at M8. And then the same thing going for some other objects. But anyway, I'll come back to some of them. I also am quite obsessed with planetary nebula. And here's a lot of the planetary nebula that you see in that area. And where to start? Well, first of all, I take away the PK catalog planetary nebula because I've so far not been able to image one of them, maybe one day. So I just stuck with these NGCs in the area. And all of these are just a few that I'm going to highlight real quick here. So way down low in Scorpius, NGC 6153 shows up kind of nice in my 8-inch, even though my 8-inch wasn't in focus on this, but next time it will be in focus. And this one was called the Bug Nebula. I didn't realize that. I just looked it up and saw it called something. So I figure it's got to be pretty interesting. It probably gets a lot of attention, but it's in the little crook of a Scorpius's tail. And then this is one showing up in my 3-inch scope as a very tiny little green dot, but when shown in the 8-inch and blown up a little bit, it comes out as a very nice planetary nebula, one to be worth doing some deep time work on. And then I'm always fascinated when a planetary nebula looks like just a little stab of green in the dark. And this one's in Sagittarius. And here's another one in Ophiuchus. And this one's with the 8-inch. And then here's another one. Oh, no, these are two. Oh, this was a great discovery. I love this. So I was looking at 6440, and then another night I was looking at 6445, and suddenly I realized, hey, wait a minute, each one is in the other's photograph. So I was able to get them both in my 8-inch Schmidt-Cassegrain grain. And next time I'm going to try to center them better, but it's kind of neat to be able to, an 8-inch scope, be able to get two objects like that, a planetary nebula and a globular cluster. And there's another little tiny planetary nebula. This one was special because it's near M28, the globular cluster. So that's the one that you see off to the right in this picture. And then here's another little green dot stab in the dark. But this one was kind of neat because it's near, it's near another globular cluster and M22. So this one here is actually the one on the left of the screen within distance of M22. So an M22 is another one of those objects we look at a lot, highly recommended, but then there's a few challenging objects you might want to hunt down near there. And then in the other direction of M22, you can also see this particular planetary nebula with a globular cluster. And so here we've got M22 again. So that M22, it's got several other things you can hunt around in that area. So anyway, globular clusters, this is the plane of the galaxy and the center of the galaxy. I've read that the globular clusters do not orbit within the same plane as the rest of the objects. So my hypothesis is that on a maybe when El Nino hits and I'm stuck inside for a long time, I'll look up the various orbits of these that are published and confirm whether they're actually doing something like I see on the screen. But it's kind of nice, fun to look at an area and just imagine, okay, everything else probably moving with the plane of the galaxy, and all of these objects are going all different cattywampus ways. Okay, a Milky Way, you go a little higher, you come to the constellation Scutum and the Shield and Aquila the Eagle. And here's some of the other Messier objects that I mentioned in the previous photograph, plus a few farther up in the sky. And there, again, there's no way I can cover all of these in the short time that's what's up, but I wanted to at least get this far because this is where I started just like 2 years ago during the pandemic, where I actually could leave my telescope out in the balcony overnight for a couple of days because everyone was working at home anyway. And it's the first time I really got good with aiming my telescope and got obsessed with these objects. And so I'm kind of coming full circle. But anyway, I'll be able to talk about some of them coming up in September. I'll be back in September. And so I shared this photograph. It's my only photograph of the whole Milky Way spanning the sky. This was in the June time. So it's the Milky Way rising. This time of year, you just have to kind of imagine it flipped a little bit on the other side. In other words, here it is rising in the east. This time of year, we think of the Milky Way starting up high, directly overhead. And then as the night progresses, we see the Milky Way actually meandering toward the west. And so all the constellations would thank you for a little visiting, and thank you for your time.
That was beautiful. If I may just say something really quick, I wanted to mention that the original composers to Pearly Shells, the original composer was John Kalapana, and then the Hawaiian was translated by Leon Probert. Thank you.
Thank you, Kim, and thank you very much, John, for yet another wonderful presentation. Totally enjoyed it.
John.
Thank you. So, hi, everybody. My name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to this general meeting of the Orange County Astronomers on August 11th, 2023. Our speaker at this meeting obtained her PhD in astrophysics from the International School for Advanced Studies in Trieste. She has a permanent research position at the Italian National Institute for Astrophysics, where she built her first research group focused on the study of black holes of different sizes. She is now full professor of computational physics at the University of Heidelberg. In 2009, several years before the first gravitational wave detection, she proposed the formation of black holes with masses about 30 to 50 times the mass of our sun. She is now an enthusiastic member of the LIGO-Virgo-CAGRA collaboration and is planning for the next generation gravitational wave detectors. Joining us 4 a.m. in the morning is Dr. Michela Mappelli. Please join me in welcoming her.
Thank you. Thank you, Reza, for this beautiful introduction. Really? Am I audible?
Yes. All good.
Excellent. So, good evening, everyone. I'm very happy. Thank you for your invitation. It's a pleasure and an honor to join this meeting. I'm sorry I'm not with you in person. It is quite a long journey from Heidelberg. But now let's talk about binary black holes. And let me see if I can change my slides. Oh, sorry. One little technical problem. Okay, so this is the outline of my talk. We will first briefly discuss what we learned from gravitational waves, and then we will focus on black hole formation, binary black holes, and we will wrap up some conclusions. So about 8 years ago, the two LIGO interferometers obtained the first direct detection of gravitational waves, which is interpreted as the merger of two black holes. Here you see this very famous picture of the first event that we could observe with LIGO. And after this first result, we had several other observations. Now LIGO and Virgo in Italy, which joined in 2017, have performed 3 observing runs, the first, the second, and the third, and the fourth one is ongoing. And as a result of these 3 runs, we have observed about 90 gravitational wave event candidates, and most of them can be interpreted as binary black holes. So now let's take one step back and let's try to see what are gravitational waves and what are black holes and binary black holes, and in which sense gravitational waves can help us to observe and understand these objects. Gravitational waves are a general relativity process that was predicted, of course, by Albert Einstein. The idea is that the presence of a massive body, for example, our planet, as you can see in this cartoon, deforms the space-time itself. So it changes the morphology of the space-time. And now, since we know that celestial bodies like our planet move around, when the massive body moves in a specific way, even the deformation of the space-time that it produces moves together with the body and propagates as a wave. It is a little bit like our everyday experience when we throw a pebble into a pond, and we do observe waves that propagate from this pond. But in this case, the waves are produced inside the space-time, and they are produced by the movement of massive, very massive celestial body. So, for example, here you see an example of 2 bodies orbiting about each other and the kind of gravitational waves that they can produce and propagate outwards from these sources. And actually, these are very peculiar waves because unlike the one that you produce in a pond of water, gravitational waves propagate at the speed of light. They are pretty difficult to observe. And in fact, we have to wait 2015 for the first direct observation of gravitational waves by LIGO And 2015 means about 100 years after the prediction by Einstein telescope. How can we observe these things and why they are so difficult to observe? Well, here I use the head of Charlie Brown to show you what is the kind of deformation that can be caused on Earth by the passage of a gravitational wave. Gravitational wave is a perturbation of the space-time itself, so it's gonna squeeze and stretch the distances between the points of the head of poor Charlie Brown. But of course, the deformation is not that big, otherwise it would be a big problem. The deformation due to the passage of gravitational waves is extremely tiny. More or less, when gravitational waves travels between the Earth and the Sun, it changes the difference, the distance between the Earth and Sun by about the size of a hydrogen atom. And here you see in centimeters, because I like to use centimeters, that the size of a hydrogen atom is of the order of 10 to the minus 8 centimeters, so extremely small, while the distance between the Earth and the Sun is about 10 to the 13 centimeters. So the distortion is extremely small, and that's the reason why it is so difficult to observe them, and we had to build a very powerful device, very powerful instrumentation like LIGO and Virgo. Another peculiarity of gravitational waves is not just that they are difficult to measure, is that they are not produced by photons. So it's not like observing photons. We are not seeing the light from celestial bodies in the universe. Rather, the frequency of gravitational waves that we observe with LIGO and Virgo ranges between a few and a few thousand hertz. So it's approximately the same frequency as the human voice. This means that when we observe gravitational waves, it's more like we are listening to our universe rather than observing our universe. So in 2015, something extraordinary happened because we, for the first time, we have listened to the sound of the universe. And I think this is really a game change, like when Galileo for the first time pointed his telescope to the sky. And if we do not just look at the light from the universe, we don't just see the light from the universe, but we also hear the sound, listen to the sound from the universe, our experience could be completely different. Now, imagine that we are traveling inside this beautiful forest, this beautiful jungle, but for some reason, we only see the beautiful light, the green trees, but we do not hear anything. And we are enjoying this jungle. And now imagine that somebody switch on the sound and we can listen to the sound that surrounds us. And then we can have a pretty peculiar experience. For example,
oh, it didn't came through.
I'm sorry, didn't. I can try to. Now we imagine that we can instantaneously start hearing the sound. And what we hear is roar from a tiger that is nowhere to be seen, but it should be very close. And this, of course, has a deep impact on our understanding of the situation, which is quite worrisome in this case, not in the general case of gravitational waves. So this experience is very important for astrophysicists. And with this, by listening at this sound of the universe, we can discover many possible sources of gravitational waves that we were not aware of before. So there are many possible sources of gravitational waves. One of them is binary black holes, and in particular, a very specific flavor of binary black holes, coalescing binary black holes. What is a binary black hole? Is a system of two black holes that orbit about each other, like the moon orbits about our planet. But in this case, we have two black holes. And at some point, we observe them coalesce, which means that we observe them getting closer and closer until they merge and become just a single black hole. As you see in this movie, of course, this is just an artist illustration because we cannot observe black holes that easily. But again, with gravitational waves, we can listen to the sound of binary black holes. And again, you can probably not listen to the sound of binary black holes right now because it did not work before. And then I will have to practice with my skills and try to do it for you. So this picture shows the signal of the first gravitational wave event, which is shown in yellow here and in blue here, as it was observed by LIGO Hanford and LIGO Livingston. And the representation shows the frequency of this gravitational wave signal as a function of the time. You see that it was a very short in time. It was just a fraction of a second. And you can see here that the signal grows in frequency from a lower frequency to a higher one. So if you could listen to it, it would be like, woo, woo. This is what we could hear, what we heard for the first time with LIGO in 2015. And that was so exciting, because we really learned a lot from this very, very short signal. The first and most important thing that we learn is that binary black holes exist. We can have two black holes, not just one, but two of them that orbit about each other. And this has been predicted by theorists, I would say many decades ago, but we had to wait for 2015 for this very short signal to have the proof of the existence of binary black holes. And here I found this very nice, as usual, cartoon from PhD Comics that pretty well summarizes my experience as a master and a PhD student. I started studying binary black holes in 2003. That was my master thesis. And for about 12 years, actually 13 years, I was studying this system without even knowing if they exist, if they are real, or just very peculiar imagination of theorists. And well, this was quite a challenge to keep our enthusiasm and keep working on binary black holes, but then you can imagine the satisfaction when in the end LIGO observed these systems, and indeed they exist, they are out there. LIGO also tells us that binary black holes can merge together via emission of gravitational waves, and this produces a single black hole that is bigger than the two progenitors. It is roughly the sum of their masses, but not exactly the sum of their masses. And also the masses of such objects can be fairly big. This first event, its mass can be reconstructed. And the mass of the two black holes seems to be 30 plus 30 times the mass of our sun. We were not expecting, most of us were not expecting the existence of such massive black holes in binary black hole systems. And now we have many of them. I'm showing you this movie, which is a representation of the masses. It's very short, so let me play it again with the masses and distance and orbital frequencies of just some of the binary compact objects that we observed with LIGO. Not all of them are black holes. So for example, this one that look blue, at least in this representation, and orbit very fast, are neutron stars. While the other, especially this one, very large, which means very massive in this representation, are very massive black holes that were really a surprise for us. And here you see a compilation of all the masses of black holes and neutron stars that we observed with gravitational waves to date. You see two different colors, dots of different colors. The size of the dots scales with the mass of the compact objects. The orange dots are black holes. The blue tiny dots are neutron stars. The gray arrows that connect three of the dots together show which binary system merged together and their remnant, which is the product of the merger. And if you are a good observer, you also see that there are a few dots that are half orange and half blue. They are not half black hole, half neutron star. Such hybrid object does not exist. Those points are half orange and half blue because we want to say with this that we do not have enough information to understand if this is just a small black hole or a massive neutron star. So the first big question that that astrophysicists try to address while considering this beautiful set of data is what are those black holes and how do they form? So let's now go through this first question. In nature, we expect at least two different types of black holes, and the only difference between these two types is their mass. We expect stellar-sized black holes. These are the ones observed by LIGO and Virgo, and are black holes which mass is similar to the mass of the stars, like our sun, but a bit bigger. With LIGO and Virgo, we have now observed black holes with mass spanning from about 3 times the mass of our sun and up to 200 times the mass of our sun. And we expect, we think that these black holes form from the collapse, from the death of a massive star. And we are going to discuss this collapse more in detail in a few seconds. But then for completeness, let me say that we also observe supermassive black holes in the universe. And when I say supermassive, I mean that their mass is larger than 1 million times the mass of our sun. At least 1 million times the mass of our sun, but we do observe objects with a mass of 1 billion times or several billion times the mass of our sun. And here, this image is a real astrophysical image. It's not an artist impression like this one. This one, if you see my mouse, is a real astrophysical image of the very center of our galaxy, of the Milky Way. These beautiful red and white dots are stars, especially massive stars at the very center of the Milky Way, in the central light year of the Milky Way. And this area right in the center, highlighted with this yellow square, corresponds to the center of the Milky Way and the location of a 4 million solar mass black hole. So in our Milky Way, we do host a supermassive black hole, as in many other galaxies. But since it is in our Milky Way, then it's relatively nearby, we can study this one supermassive black hole much better than the others. But this is another talk, so now let's focus on the stellar-sized black holes that LIGO and Virgo observed. And let's try to understand how do they form from stars, why a star at some point in its life should decide to become a black hole. A star is, the simplest possible description of a star is just a sphere of gas. And this sphere of gas can exist for several million years or several billion years because it is in equilibrium. In equilibrium means equilibrium between the gravity force, which tends to make it collapse on its own, and it is because the star is massive, and the pressure of the gas that instead counterbalances the gravity force and tends to make the star expand. Since they perfectly balance in a star, or almost perfectly balance, the star can be in equilibrium, and we observe it for many, many years. You can understand what is the source of gravity. It is the mass of the star. But what is the source of the pressure of gas? It is basically nuclear reactions. The nuclear fuel that powers, that is the engine of the star, of the stellar photon. But the nuclear fuel is not infinite. So at some point when it is over, the star just collapses because its gravity is still there, but the fuel that powers gas pressure is no longer there. So nothing can keep the star in equilibrium anymore. And this is when a black hole forms, when the star cannot stay in equilibrium anymore. Actually, this formation can produce very beautiful transient processes, very beautiful objects in the sky. Because when a massive star, more than 8 times, roughly more than 8 times the mass of our sun, runs out of its nuclear fuel and starts to collapse, the first result of the collapse is an explosion because of the shock generated, triggered by the collapse. And then we do observe these beautiful explosions that we call supernova explosions. And here you see 3 examples of supernova explosions that we can observe here. This is not the time of the explosion. This is the remnant of the explosion, the photons that represent the fossil photons of the explosion that we can still observe. And again, these are not artist impression. These very beautiful images are astrophysical images that were taken with telescopes. A supernova explosion is one of the most powerful events, astrophysical events that we can witness. About 10 to the 51 erg are released just in a few seconds. Well, astrophysicists astrophysicists use these very weird units, physical units. But to give you an idea to something that you are probably more familiar with, which is, for example, a nuclear plant. A typical, I would say even smallish nuclear plant is about 1,000 million watts. This corresponds to about 10 to the 16 erg per second. This means that a supernova explosion emits just in a few seconds the same energy as a small nuclear plant in 10 to the 27 years. If we think that the age of the universe is roughly 10 to the 10 years, it means that there is no time for the nuclear plant to produce the same energy as a single supernova in a few seconds. After a supernova, which basically the supernova removes the outer layer of the star, the skin of the star, what remains at the center of the supernova, the remnant of the star, is usually a very compact object. When an astrophysicist says a compact object, it means something that is still very massive, but small, so extremely dense. These small and massive objects could be either a black hole or a neutron star. To give you an example, the density of a neutron star is about 10 to the 17 kilograms per cubic meter. And the density of our planet, for comparison, is just 10 to the 3 kilograms per cubic meter. But the radius, vice versa, the radius of our Earth is much, much larger than the typical radius of a neutron star. Here you see this image of our Earth, and here you see a very small dots. And this is how a neutron star would appear in the same scale, because the radius of our Earth is about 6,000 kilometers, while the typical radius of a neutron star is just 10 kilometers. Even if the neutron star has approximately the mass of our sun, so it's much, much more massive than our planet. So we have learned now that a supernova explosion expels most of the outer layer of the star that explodes. So if the supernova explosion takes place, the final neutron star or black hole that forms will have a low mass, relatively low mass, because most of the mass of the star is lost during the supernova. And in fact, if we run some calculations, very complex calculation is called a simulation of a supernova explosion, and we try to estimate the final mass of the compact object, we find something like 1.5 times the mass of the sun for a neutron star, and only about 5 times the mass of the sun for a black hole. So we only form a low mass black hole when the supernova takes place. But with LIGO and Virgo, we have observed black holes with a mass that is 30 times the mass of the sun. So how can we form this very massive black hole? This has been a puzzle for many years. So how can we form such massive object from the collapse of a star? The best solution that we found, which is still work in progress, so it may be that if I give this talk again in a few years, I tell a completely different story. The best understanding that we have now is that these massive black holes should not come from a successful supernova explosion. They cannot come from a successful supernova explosion. Rather, we expect them to come from the collapse, the silent collapse of a star without any explosion. Basically, all the star implodes onto its own center. How is it possible that some stars decide to explode when their life is over, when their nuclear fuel is over, and other stars just do not? The possibility is connected with the idea of escape velocity. If we can launch the outer layer of the star fast enough so that they can unbind for the rest of the star, that their velocity with which they leave the surface of the star is higher than the escape velocity from the gravity of the star, then they are lost forever. But if this is not the case, then if this is not the case, then if we cannot launch the outer layer of the star fast enough, then they should fall back onto the star. This is pretty much similar to the calculation that we need when we want to launch a rocket or a satellite from the surface of our planet. We want its speed to be higher than the escape velocity of our planet in order to stay in orbit and not fall back onto our Earth. Same during a supernova. If the velocity of the outer layers that are ejected by the explosion is not high enough, these outer layers will fall back onto the star and just collapse, producing a possibly very massive black hole. Here, I am very proud to say that this is what we have been worked on with our group for several years. So here I'm just showing you a recent image of our group with many young and enthusiastic researchers. We studied the possibility that massive stars can collapse without any explosion. And we produced some models that predict and helped us to explain what we observed with gravitational waves. But now, since time is running quite fast, we have another problem to solve, an even bigger problem. Okay, but now you can tell me, you have told us more or less how we can form a single black hole from the collapse of a single star. LIGO and Virgo observed 2 of them orbiting about each other with a very short orbital separation. So how can we produce these binary monsters? So the next and last question we will discuss is, how do we form a binary black hole like the one that we observe with LIGO and Virgo? There are many possible theories. I will just briefly mention the 2 main theories. Sorry, a wasp is participating to my talk. Go away, little lady. The simplest idea is we know that stars can form in binary system. We observe many of them in binary system. So what if a massive binary star evolves and at the end of its evolution produces a binary black hole? Yeah, indeed, this is a very good explanation. The problem for astrophysicists is that the life of a massive binary star is extremely complicated. There are many processes that affect the evolution of these 2 stars that can completely change their final fate and the formation of the binary black hole. For example, here you can see some very nice artist image of what happens when 2 massive stars are sufficiently close that they decide to exchange mass to each other. And this can lead either to the merger of the 2 stars. The 2 stars, one of the 2 stars is basically completely disrupted and swallowed up by the other star. Here I hope that this movie plays, because it's a very nice artist movie based on a astrophysical simulation showing 2 massive stars. The colors and the size of the 2 massive stars are physically motivated. They are based on a simulation. Now they just orbit about each other quietly, but at some point you see that something happens, weird happens, that here it is, one of the 2 stars decides to transfer mass to the other. And you will see that the shape, the structure, and the color of the 2 stars changes completely because of this process, until the orbital properties are completely disrupted and our binary basically dies. So one of the 2 stars leaves the other and then puffs up as a giant star and explodes as a supernova. The other one also evolves later on and also produce a supernova, but this will not be a system that we observe with LIGO and Virgo, because mass transfer has disrupted the system. And this is how we lose most of the binary system. So binary evolution is one of the main processes that can explain the formation of binary black holes. But there is even another one, that is the dynamical formation. It's even more fun, if you want. How can we form a binary black hole dynamically? In our solar neighborhood, stars are really far away from each other. And this is good, because if our sun was very close to many other stars, we could be in trouble. Maybe we would not be here to discuss tonight. Because when the density of stars is really high, the stars are close enough to interact gravitationally with each other. It's quite intuitive. If we put about 50 people in a very small room and the people start running around, it's very likely that they interact with each other and they get closer. If we only have 5 people in the same room, they can go around without necessarily passing by. This is even more true for stars, because stars just do not know about each other, so they cannot avoid the encounter and the collision with other stars. And where are these environments, these very dense rooms where we can pack stars together and force them to interact? For example, globular clusters. I'm very happy we have seen these spectacular images of globular clusters during the WhatsApp, because really globular clusters are fascinating systems for astrophysicists for a very large number of reasons. And one of them is that they could be a factory of binary black holes. Actually, we think that they are a factory of binary black holes. In globular clusters, the density of stars is 4, 5, 6 orders of magnitude higher than the density of stars in our solar neighborhood. So not only stars interact with each other, but even black holes can interact with each other. And so, for example, they can pair up with other black holes. This can happen not only in globular clusters, but also in youngster clusters. Here you see a beautiful image, astrophysical image of a youngster cluster that is still enshrouded in gas, and other clusters in the universe. So what kind of interaction can bring 2 black holes together so that they pair dynamically up, they form a binary? One example is a dynamical exchange that we think happen all the time in a globular cluster. Imagine that we have a binary star that here is shown in red. This is an astrophysical simulation. And then a black hole that here is shown in blue. And they have a close encounter like this one that is very chaotic. And so the binary orbit is perturbed. And at some point, you see the formation of a new binary system with the black hole in blue and the star, while the other star is first perturbed and then ejected from the system. So what happens is basically that if we start with a binary system composed of a black hole and a low mass star, in a very dense stellar cluster, this system can interact with another black hole and produce a binary black hole. And we think that is very common, this scenario. So now let's try to wrap up what we discussed. We have seen that there are multiple possible ways to produce a binary black hole. One is with the binary evolution of stars. The other one is with the dynamical interactions. How can we explain what of these channels explains the formation of the binary black holes that we observe with LIGO and Virgo? The honest answer is we do not know. We do not know yet. But for example, with numerical models, we see that dynamical encounters explain the formation of the most massive black holes more easily than the binary evolution. And we can have all a zoology, full zoo of dynamical interactions, like multiple collisions of stars that here we represent with this nice cartoon from one of our simulation, or even hierarchical mergers of black holes. So multiple black holes that merge after one another in a dense stellar cluster. So again, do LIGO, Virgo, and now Kagra in Japan observe black holes that form from dynamical interactions or binary evolution? We do not know yet, but now the 4th LIGO observing run is ongoing. And then we will have new candidates soon, and this will definitely help us to understand who is the culprit, what mechanism produces the binary black holes that we observe. So I'm done. Thank you very much for your attention. I hope I'm not late. And now I will be super happy to address your questions.
Thank you very much, Michela. That was a fascinating talk. Great, great. I already see questions are coming your way. And I hope you could see the kudos coming your way in Zoom as well. Great, thank you very much. So let's go to the questions. Now, the whole talk is about binary black holes and then how they merge. So the question is, at what point does the ring down, when their orbits shrinks and shrinks until they collapse, become stable enough to consider the system a single black hole? You know, when one is the exact point of merger, let's say.
Oh, wow. This is a technical question from a colleague, I would say. Excellent. So I didn't describe the process of merger. So usually we distinguish the process of merger in 3 stages. It is, of course, there is a continuum from one another. It's more a classification that we use to make our life easier when we simulate them. So first we have the so-called in spiral, when the 2 black holes are still orbiting around each other in a binary system. And then they approach close enough that they start fusing together, they merge together, and this is the merger stage. But then when the 2 black holes merge together, because they were moving around each other, they do not just produce a stable and nice and perfect black hole immediately. We should imagine that the merger product, the new black hole, is a bit of equilibrium when it forms, and so it starts oscillating while trying to reach its equilibrium configuration. And this is a general relativity process, so pretty difficult to model with simulation. But I can tell you that this is a very complex process, but also very fast. I showed you at the beginning, let me see, it does not take too much to go there, that yeah, it takes too much because I get stuck here. Here, good. That the whole merger system only takes a fraction of a second. Well, the ring down is a fraction of that fraction of a second. So it's really, really just a point in this image. On the other hand, it's a point that is very important because it could, if we add constraints on it, it will tell us a lot of information about the black holes, their natures, and the neutron stars. So it's very short, but very important, I'd say.
Perfect, thank you. Now, going back to the last slides of your presentation, you showed us this hierarchy of black holes that could merge and merge again and merge again. Now, there's this question. All the mergers that you showed were 2 black holes merging, and then the result later merging with another black hole. Can more than 2 black holes simultaneously merge? Has that been studied?
Wow, real difficult question. Maybe I should have done a more complex talk. Sorry, I have problems that my presentation just crashed, and I know this is embarrassing because I'm a professor of computational physics and I cannot put my presentation together and prevent it from crashing. So multiple mergers of black holes. This is real interesting. Indeed, we expect that black holes can merge repeatedly. However, the probability that two black holes merge exactly at the same time, and I'm sorry, I hope you can still hear me because now the presentation is frozen. Okay, so I cannot go to my last slide right now. Sorry. We do expect that black holes can merge repeatedly, but the probability that more than two merge at the same time is terribly low, is negligibly low, even in a stellar cluster. We expect it to be like less than 1 in a billion. On the other hand, and this is one of the frontiers, I would say, of future detectors, the Einstein telescope, the cosmic explorers that will start taking data hopefully in 10 years, 15 years from now. They will be able to probe also the early universe, the universe close to the Big Bang. In that case, the density of black holes could be very high, that these simultaneous multiple mergers could even be observed, but we would be very lucky anyway.
Great, thank you. Okay, now let's switch to the in-person audience on the ground. Are there any questions from the people at Chapman?
Okay, let's see, any questions? Yes, we're clear here.
Okay, so let's go back to some questions from the online audience, and then we'll get back there. So the next question is about the recent nanograph discoveries. Can you comment on those and briefly tell us about them also, please?
Oh, that's fantastic. Is really potentially a game change. Thank you for this question, really, because I quickly mentioned here that there are two flavors of black holes, the stellar size ones and the supermassive black holes. And also what I didn't have time to mention, that even two supermassive black holes can form a binary system that orbits about each other and can merge, producing gravitational waves. But since the mass of the two black holes is so different, these gravitational waves have a very different frequency too. They are not in the frequency range of human voice, a few hertz, a few thousand hertz. Rather, they are in the frequency range of the 10 to the minus 2, 10 to the minus 3, or even 10 to the minus 6, 7, 8 hertz. And then we cannot observe them with LIGO and Virgo. We need something very different. And the nanograph observation is exactly that, is the first glimpse of a gravitational wave signal that is at the right frequency to be produced by supermassive black hole mergers. For people who are not familiar with nanograph, this is a very beautiful, I think, experiment, because it's one of the few cases in which you can use astrophysical objects themselves as telescopes. From the Earth, we observe pulsars that are neutron stars emitting in radio with the radio telescope. Those pulsars, for their nature, are extremely precise clocks. They emit pulsating radiation that is very, very precise. And when a gravitational wave from something else, from another astrophysical body, goes through the neutron stars, the pulsars, basically it changes the location of the pulsar on the sky a little bit. And it also changes the time of arrival of the pulsar pulse to Earth. So if we observe multiple pulsars at the same time, we see that something is going on, something weird is going on with their pulses that are usually very precise. And we can reconstruct that this something is gravitational waves emitted, for example, by supermassive black hole. So Nanograph is expecting to see a signal from a supermassive black hole merger from these pulsar observations. What has been discovered, though, is not a single supermassive black hole merger yet, is rather the cumulative and not resolved contribution of all these supermassive black holes that are not loud enough for us to hear them directly with the pulsars, but we can hear them all together. And this is fascinating because it's really the first time that we have a proof of these supermassive black hole binary mergers.
Perfect. Thank you very much. Now, in your talk, you did mention that the gravitational waves are going to be traveling with the speed of light. Now, this question has two aspects to it. First of all, has there been a simultaneous observation of the same phenomena in electromagnetic waves, and have they been correlated? And then, thus, has it been experimentally confirmed that gravitational waves do indeed travel at the speed of light?
Oh, super. Another super good question and very technical too. I will answer the second part first because it's short. Yes, indeed. With gravitational wave observation, we can also constrain whether they actually move at the speed of light, and the agreement is terribly good. So indeed, Einstein was right. Also in this case, gravitational waves do travel at the speed of light. As far as we can constrain them. And the simultaneous observation of electromagnetic emission. To my fault here that I do not have a slide about 170817, the first binary neutron star merger. So not only black holes can merge, but also neutron star can merge together after orbiting about each other. It is this one. These two little dots, let me see if the movie plays again, that orbit about each other with this very high frequency. When we do observe the merger of two neutron stars, the situation is very different from the merger of two black holes. It is similar in the sense that we do expect gravitational waves, and we have observed them. But since neutron stars still have some matter, although very strange, very peculiar matter, but they still have matter. During their merger, some of this matter can be ejected, can be lost, and produce electromagnetic radiation. And this is what we observed for this specific case. Unfortunately, not for the others because they were much farther away, more difficult to observe. But in the case of 170817, we did observe a faint gamma ray burst connected and a kilonova, what the astrophysicists call a kilonova, connected with this source, which is basically the electromagnetic signature of the merger. And this also gives us constraints on the distance of this event, on the properties of the host galaxies, because we did observe the host galaxy of the system, and so many other beautiful pieces of the puzzle that we can put together.
Perfect. Thank you very much. Now, since we are on this slide, which represents is that all or a lot of the, or a sample of the events observed by the gravitational wave detectors? Can you tell us about how far they are? Have there been any inside our galaxy, or are they all on other galaxies far away?
Super. So no, this is a selection, actually. These are the events that we observed in the first observing run. Their name, this phone number, also tells when we observe them. So these are from 2015, the first observing run. Then these are from 2017, the second observing run. And then here starts the 2019, which is the first part of the third observing run. And from now to the end, you see the first part of the third observing run. And then there is a second part of the third observing run that is about 30 additional events. I don't remember the number. Before I kept the count religiously. Now instead I start to say, okay, about 100. And now if you go to the LIGO and Virgo webpage, you can see already the alerts of the new events that have been observed in in 04, which is running since the end of May. So there are already new events, although we are of course running the analysis to see if which of these events indeed are astrophysical. How far are they? LIGO and Virgo observe our universe. Well, here it depends on if you talk to a cosmologist or to an astrophysicist. I would say that they observe a small part of our universe. Astrophysicists use redshift to indicate cosmological distance. LIGO and Virgo now observe system up to redshift 1. What is redshift 1? Well, to give you a comparison, the most far away objects that we observe now in the universe are at redshift 10 or even more. So redshift 1 is pretty local. But still, this allows us also to trace the evolution of this system. Do we observe some of them from the galaxy? No, just because our galaxy is very small with respect to the universe. When I say that redshift 1 is small, I mean small with respect to this history of our universe, the life of our universe, but this encloses already several box of several billions of light years. So our Milky Way is really only, I would say, a few thousands of light years across. So we do expect binary black holes in our Milky Way, but since the process that brings to their merger is very rare, we do not expect that any of them inside the Milky Way is merging right now. We would be too lucky to have a merger right here, right now.
Okay, yes, let's hope that happens. Although it might have some electromagnetic effects that are undesirable. Okay.
Well, if it is binary black holes, they are pretty quiet and nice guys, so probably we would just enjoy it.
Okay, excellent. So now we talked about gravitational wave detectors. We have Virgo, LIGO, and then now Karga is being added also. Do you have any information on LISA, the Laser Interferometer Space Antenna? Do you know when it's going to be online?
Oh, Lisa, cool. Well, a good point, because there is still a decision to be made whether the mission will be actually adopted by the European Space Agency or not. But we all hope that it will be a huge yes, adopted. And the expected time is if I remember, is 2035. So this will be very exciting if this happens, because it means that we will have the first space-borne detector together with the next generation ground-based detectors, the Einstein Telescope and the Cosmic Explorer. They will happen, all of them, between 2035, 2040. So this opens a number of exciting possibilities, because LISA will be observing mostly supermassive black hole mergers, similar to the one of nanograph, but a little bit less massive. Well, less massive supermassive black hole is kind of weird, but let's say 10 to the 4 to 10 to the 7 solar masses. This is what I mean for smaller than nanograph. But LISA will also observe these stellar size black holes weeks or months before their merger. So the idea is that maybe with LISA, we can observe one binary black hole very nearby when it is still weeks or months or years before its merger. And then with the Einstein Telescope and a Cosmic Explorer on Earth, we can measure it again a few years later, while at the exact time of the merger. So we could do what we call multi-band gravitational wave astronomy.
Perfect. Thank you very much. Now let's switch to the crew on the ground. Any questions from Chapman?
No, no questions.
Okay, so let's switch again to the online audience. You showed us how the mass transfer between the two binary stars can work, and how one of them is going to go supernova first and then the other one. Can you tell us a little bit more about this process? Will the mass transfer trigger one of them to go supernova, or it's just not related?
Oh, wow. This is another excellent question. Actually, something we are working on right now. Yeah, the mass transfer is one of the big question mark when studying binary evolution, stellar evolution, not only binary black holes. It does not speed up or triggers the supernova, but what happens is that it changes the mass of the accretor. The accretor is the star that receives the mass. So if the accretor can accrete this mass significantly, its subsequent stellar evolution will be perturbed, and this affects the way it dies, if it dies with a supernova or with a direct collapse, the kind of light that we observe from this star before the supernova. So it could be a blue supergiant or a yellow supergiant or red supergiant right before it dies. It's not gonna change that much the stellar life. So it's not gonna affect the onset of the supernova. It's rather the opposite, that mass transfer usually in stars takes place when the star radius changes rapidly. Because if two stars are separated and they are not in contact, their radii don't touch, roughly speaking, then they do not exchange mass. But the stellar radii change during the life of the star. And this happens when the inner stellar structure changes. When usually when you go from burning hydrogen in the core to burning hydrogen in a shell. At that point, the radius of the star usually puffs up, and then two stars that were not touching each other before, they start being in contact, they start touching. And so mass is transferred. This is why in that movie, you see that the supernovae happen right after mass transfer, because mass transfer happens in those phases of the life of the star where there is a transition from one nuclear burning to another and the stellar radius changes that usually are also close to the final explosion of the star. I hope this was kind of
Very
understandable because it
interesting.
was probably
Thank
the
you.
most technical thing.
Yeah, sure. So now the other question actually relates to the same slide that you're on. Can you comment on the velocity at which these binaries are rotating? Does it only depend on their distance or their masses, or maybe they have some initial velocity before?
Their velocity is set by their orbit. It's the same as for the system composed of the moon and the earth and the sun and the earth. And it's basically, in principle, it is just Kepler laws. If I know the mass of the earth, the mass of the moon, and I know their distance, I can calculate their orbit and I can calculate their orbital speed, which is pretty easy if we assume a circular orbit. For these black holes, it is the same when they are sufficiently far apart. But when I say sufficiently far apart, even a few seconds from the merger, they are sufficiently far apart. So it's only when they really are at the point of the merger that general relativity corrections take over. And then we cannot define this as a binary anymore. And we need to switch to a more sophisticated treatment, like general relativity hydrodynamical simulation. When the two black holes are still orbiting about each other, we can calculate their orbital velocity, their orbital frequency with Kepler law, and we make just a little mistake. And there is a very nice feature that if you do the math, you find out that the orbital frequency and the gravitational waves frequency are related by a very simple relationship. The gravitational wave frequency being about twice the orbital frequency. So from Kepler laws, we can derive the orbital frequency, and from the orbital frequency, we can derive the gravitational wave frequency. So you can look at this and figure out what is the orbital frequency of these binary systems.
Perfect, thank you. And looks like this is the last question. Now, the questioner has a picture of what the gravitational wave looks like, and he wants it to verify. So the question says that they have been picturing gravity waves as just the variation of observed gravitational strains due to an object or objects rapidly varying its distance. Is this a correct image that they have in their mind? Can we measure the gravitational pull versus distance, or you're doing it other way?
The distance of the two bodies is a key point here. Let me try to avoid too technical things, but I'm happy I'm on this slide because here below you can see this yellow line here, and this yellow line and this blue line down here. This is how the modulation of the gravitational wave signal looked like. And you can see that at this point that is put in correspondence to the merger, the modulation leads to the largest amplitude. So the distance between the peak and the minimum here is the largest. And also the frequency, so the distance between two peaks gets smaller. So here you have three peaks that are closely packed together. Here you have the same three peaks that are closely packed together. Instead here, well before the merger, you see that it's even difficult to see the modulation because the amplitude of the signal of the wave is very small, and also the peaks of the waves, this one, for example, this one, are more spaced in time. So the picture, this is exactly from the data. These are data, analyzed data of LIGO and Virgo. They confirm the picture that we have from the theory, that when the two objects are about to merge, the two black holes are about to merge, their distance becomes smaller and smaller. When their distance becomes smaller and smaller, the frequency of gravitational waves becomes higher and higher. This is what we see when we see that the distance between the peaks gets shorter and shorter. And then also when they get closer to each other, the strength of gravitational waves that are emitted becomes louder. The gravitational waves becomes louder. So the peaks, the strains become higher and higher. Here we have a very small difference between the maximum and the minimum. Here we have a larger difference. So this is exactly right. When the two bodies get closer, the power emitted in gravitational waves becomes higher. And so the strain that we observe, which is the distance between the maximum and the minimum, gets larger. And the frequency gets higher. So in time, this means that in times the distance between the two peaks gets shorter.
Perfect. Thank you very much for yet another explanation of this wave that we see. Here we have another question also. Now this time about the effect that the expansion of the universe might have on gravitational waves. So has there been any analysis to what effect the expanding universe would have on a gravitational wave as it travels large distances?
This leads to a very good point that as all the other messengers, so for example, the photons, also gravitational waves feel the expansion of the universe and the redshift so the Doppler shift basically of the signal. This means, for example, that we can probe the Hubble law. I don't know if you are familiar with the Hubble law, also with gravitational waves. The expansion of the universe as it was originally depicted by Hubble is basically that we can link the velocity at which the objects separate from each other to the distance between each other via a constant that we call Hubble constant. And one of the main goals of cosmologists, and I would say astrophysicists, is to get a good measurement of this Hubble constant to understand how much the universe expands, because maybe some of you are aware, well, you seem very well prepared, so I think all of you are aware that there is a possible problem between the measurement of the Hubble constant that we have from the cosmic microwave background and the one that we have from electromagnetic indicators like the supernova. With gravitational waves, we could in principle break this degeneracy because we can use the measurement of the redshift, in this case, not directly the redshift, it's what we call the luminosity distance that we obtain from the reconstruction of the gravitational wave signal. And then if we have an independent measurement of the distance of the gravitational wave's end that comes, for example, from the detection of the electromagnetic counterpart of the host galaxy, we have the two terms, all the two terms that we need in Hubble equation to reconstruct the Hubble constant. And this has been done especially for the binary neutron star merger we were discussing before. It has been done to a very accurate, in a very accurate way. And this represents a third and independent measurement of the expansion of the universe that now is still a bit not good enough with just one neutron star to understand who is right, what is the value of the Hubble constant, but in the next few years with more detections, it will become better and better and will allow us to understand the expansion of the universe.
Thank you. Thank you. So let's do a last call for questions from Chapman. Looks like there is one.
I have a question here.
Several people in the room, as well as myself, were so impressed with your sound effects when you did that merger sound. I mean, it really sounded like ones I've heard done. So that was awesome.
Yes,
Oh, thank you. Thank you. Thank you. Yeah, actually, there is this legend, which is not just a legend, that if you want to join the LIGO Virgo and Kagra collaboration, you have to prove that you are able to do that sound good enough. So yeah, it's hours and hours of practice.
Great, great. So we also was that all comments from the Chapman? Any other questions?
Any other questions or comments? I think this is it.
Perfect. So we are almost out of time. We have even more questions. So let me briefly mention them. First of all, about Hawking radiation. Can that help to study binary joiners, mergers? And in addition to oscillations in the space and time, would there be any oscillations in matter as the black holes begin to merge? So that was two questions I asked simultaneously.
Yeah,
maybe,
very briefly, if you want. Hawking radiation, yeah, can be very useful to understand black holes, and we can use what we see from gravitational waves to constrain it, because if we start probing also other frequencies, we could start probe other black hole masses and black hole formation scenarios. Oscillations in matter, actually there is conversion of matter to energy during the merger, and it's very difficult to do this measurement even with current detectors, so we cannot really claim that we observed it, but the estimate of the amount of energy that is produced during the merger of two black holes, for example the massive event 1905-21, tells us that this is the most energetic event that we observed after the Big Bang.
Perfect. Thank you very much. And as the last question, a lot of scientific projects do have some, let's say, citizen science aspect to them. So are there any websites established for gravitational wave detection that citizens can get the data and help scientists process them?
Oh, super excellent question. Indeed, there is a public website with the alerts, which does not contain the raw data, just the alerts, because the policy of LIGO Virgo is to make the data available after publication. The reduction of this data is highly not intuitive, and this is now the big problem, and it will become even more a problem with the next generation telescope, because this is a weird kind of data. Usually when we have astrophysical data, we have the signal that could be observed, that could be seen even by eye, even before reducing the data, and then the background, which we can clean one way or another. In gravitational wave data, usually the background is 10 times higher than the signal. So the reduction of these data is a challenge, both for the tools that one needs to use and for the computational power. But yeah, it's definitely interesting to start thinking if a community effort could help us to solve the problem that will become even bigger of analyzing this data with the new detectors.
Thank you very much. So Dr. Mappelli, thank you again very much for a wonderful talk. Thoroughly enjoyed it, and I thank you for answering all our questions. Now I would like to also thank all the attendees for their presence and participation, for excellent questions. So please check the calendar on our website for all our upcoming events at ocastronomers.org. Thank you again for joining us, and we wish you great times ahead. Bye-bye, everybody.
Thank you for the great questions, and thank you